Welcome. I want to talk again about the Cauchy Central limit theorem. Here it is. It is a result about independent random variables with the same distribution. So this density doesn't need to be absolutely continuous. It doesn't need to be a function. It can be a measure. But we want that the mean exists in a Cauchy sense, and we want to have this risk value, this asymptotic growth of the variance if the expectation is 0. We want this to be to exist, and in that case we have a convergence to the Cauchy distribution. So this week I was looking at a little bit more at the details. There is a little bit of Fourier theory involved, and I was also looking at the history, more at the history. So when you're doing research, there are two kind of difficulties. One of the difficulties is that you have to have the math right and something new. And the second thing is that you have to beat the history. So in this case, these are hundreds of years of research. And actually I discovered also when looking at the literature that these generalized central limit theorems have been developed very early on already. Cauchy was looking at it, wanted to explore the counterexamples to the central limit theorem. And maybe a kind of a very important figure in this area of generalized central limit theorems is Paul Levy, who looked at the very general setup. You can do that with m to the alpha with some, alpha is equal to 0 would correspond to the usual case when we have bounded variation. That's the standard case. I like the case of the Cauchy case because it is very explicit. Everything is nice. Then maybe there's a book of Kolmogorov and Nidenko which mentions also a central limit theorem of this type, but it makes assumptions on the cumulative distribution functions. Levy just looks at the Fourier transform, conditions on the Fourier transform, what we have looked at last time. If the Fourier transform has this property that it's kind of this shape where you have kind of where you have a derivative to the left and derivative to the right, then it's in the domain of attraction of the corresponding distribution, stable distribution. That's what Levy realized, and it's easy to show using this functional equation that you have a contraction in that space. We actually want to link this condition here to the Fourier transform, to the characteristic function. So I at the moment think this is new. Maybe not that exciting than I initially expected, because there are similar results have been already obtained. So from a pedagogical point of view, an interesting topic, and shows that calculus is very, very important in statistics. I mentioned this already last time. If you look at the list of these are maybe today you would call them statisticians, but they were of course mathematicians and very, very, very good analysts. So they were you would think, why does Dirichlet think about these things? And Dirichlet was more in number theory. But if you look at him, kind of, this is the Cauchy distribution, a very important distribution, very important functions in calculus, because, the antiderivative of this, arctan, the Basel distribution, that's kind of one of my favorite, which belongs to that. That actually kind of implies directly for that. I call this the Basel distribution, the zeta distribution. So you take the zeta function a to the k to the s, and then you divide by zeta to the s. That of course is a distribution, but you can symmetrize it so that you have this property here. So if you look at this, then the Cauchy, the limit in the Cauchy sense exists. Very interested also in kind of these special functions like the polylog. We have looked at that with Lesieutre. These are Dirichlet series, and interesting Dirichlet series appear here when you look at the Fourier transform, like the polylog, which generalizes the log function. So there are Pareto distributions which have been studied first by an Italian mathematician, also wrote interesting books about how the elite develops, very interesting sociology, and he looked at the wealth distributions and saw some power laws, but that's a kind of a simple example which you kind of might like in calculus, that you have a 1 over x squared decay on both sides, and also here kind of, when you multiply by x squared, of course that doesn't converge, but obviously this converges here. So these distributions are all in that class. I like this condition here because you don't have to kind of compute the cumulative distribution function of your density. You can just use the density alone, and you also don't have to compute the Fourier transform, which is the distribution function. The history is very interesting. There are nice resources. I'm starting to write down this note about this Cauchy Central limit theorem. This condition, we have to show that this condition actually gives us a left or right limit of the derivative at 0. So this distribution function is it's continuous, but it's not differentiable. And actually here, for example, if you look at the Basel thing, so this looks kind of some if you look at this polylog thing, it looks maybe something like that. So it has this typical cusp, like non-differentiability, and so this function phi is always between -1 and 1. It's kind of obvious, and it's also uniformly continuous. So the function is continuous, uniformly continuous even, but it's not necessarily differentiable, and actually just at that point 0. It's never differentiable if you have this Cauchy case. So there is this thing, but we have to show, and that's kind of the goal, in order to be in that attractor of Levy. Levy, was first who saw actually that this would be and maybe even, Cauchy also looked at the Fourier transform already, or the Laplace transform. So Cauchy, of course, had already also the complex numbers available. So if you take the Laplace transform and you complexify it, you get the Fourier transform. So also Poisson was very interested in Fourier transform. So this is a playground for Fourier theory. And what we have is a very, very clear mathematical problem. So we have this limit exists and this limit exists, and we have to make a statement about the behavior of the Fourier transform at 0. So what we have to show is that the limit here from the left exists is c, and from the right it's -c has to exist. Cool, that's it for today.